Good morning, everyone. So we find vulnerabilities in programs, and we write exploits to take advantage of those vulnerabilities. However, writing an exploit is actually like an art, which is time-consuming, even for skillful hackers. So once we capture an exploit, it will be great if we can just reuse it without manually analyzing it and developing a new one by ourselves. But how can we do that? How can we easily reuse their exploits? I'm Tiffany, and today I'm going to present our work. Your exploit is my automatic shellcode transplant for remote exploits. This is joint work with Fish Wang, Jan Shostashvili, and David Bromley. We are from Carnegie Mellon University and UC Santa Barbara. Okay, let's start. There are many different kinds of exploits. There are denial of service exploits, web application exploits, and remote exploits. In our talk, we are going to focus on a particular kind of remote exploits, which is also one of the most dangerous exploits. We call it control flow hijacking exploit. A control flow hijacking exploit is an input that deviates the control flow of the program and leads the program to carry out the malicious computation controlled by the attacker. The malicious computation is the payload of the control flow hijacking exploit, and we call it shellcode. Different people have different purposes of attacking, and thus they will have different shellcode. Yep, this is shellcode. For example, suppose we have an exploit from the others, and their shellcode is to steal a file for their shellcode. However, our own shellcode is to install malware. So to reuse the existing exploit, we need to change the shellcode to ours, and we call it Shellcode Transplant. After first glance, it seems that Shellcode Transplant is easy. All you need to do is to strip out the original exploit and put your own shellcode to the existing exploit. However, the shellcode that is actually executed may not be exactly the same as what we see in the exploit. When a program processes an exploit as an input, it may change the input bytes to other values. In order to generate a new successful exploit, we need to figure out how the program processes this input so that after processing, we will get the expected shellcode in the end. To identify how the program processes this input, previous work uses symbolic execution, where it assigns the input to symbols and execute this program acts symbolically until the program goes to the exploitable state, where we're about to start executing the shellcode. Well, you see, this is pretty dangerous code, so the skin goes dark a little bit. It's just, yeah, it's cool. All right. Okay, let me continue. So now we're at the exploitable state, and the second step is to concretize the input with the replacement shellcode. From the first step, we will have the path constraints, which is the constraint for letting the program to reach the exploitable state. And for the second part, we get the shellcode constraints, which requires the program to execute exactly what we want for shellcode. And finally, we could solve the constraint, get a satisfiable solution, and that can be used as an exploit. However, there may not exist a satisfiable solution. For example, suppose we have a vulnerable program saying only if sk is equal to 2, it goes to a vulnerable function. And in this case, to trigger the vulnerability, we have to have sk is equal to 2. On the other hand, when we concretize the shellcode to the symbolic memory, we may have some constraints saying, well, sk has to be equal to 1. These two constraints are contradict. And another possibility is that there is still a contradiction between the path constraints and the shellcode constraints. However, the path constraints may not be necessary to trigger the vulnerability. For example, suppose we have this piece of this source code, and we have if sk is equal to 2, it does blah, and then it calls a vulnerable function. In this case, we doesn't have to make sk is equal to 2. However, when we do symbolic execution, the symbolic trace goes into this if statement and come up with this constraint saying sk is equal to 2. So the question is, how are we going to resolve those contradictions? So we propose our work, shell swap, which is based on symbolic execution. And in addition, we propose two methods to resolve those contradictions. The first method is called path knitting, which is basically to change the path constraints. And the second is called layout remediation, which is to change the shellcode constraints. We'll start with layout remediation first. Layout remediation is to change the shellcode constraints by changing the shellcode layout in the memory. Traditionally, we view shellcode as an entire chunk composed by instructions. However, we can view it another way. Why don't we just separate those instructions and link them by jump instruction? In this way, we can come up with different layouts. To try the different layouts, we're going to do it in the following way. We'll start with the first instruction, try to locate it in the memory, and see how the constraints goes. If so far we still have a satisfiable solution, then we're happy, we're going to continue. If not, we're going to relocate the first instruction. Suppose we are happy, and let's come to the next instruction. Now, when we try to put the next instruction into the memory, we realize that, well, there is a shellcode constraint which is contradict with the path constraints. So we cannot locate the second instruction there. What are we going to do? We're going to try to find a jump instruction located after the first instruction and see if the jump instruction fits with the original layout. And if it does, we will continue locating the rest of these instructions. And in the end, we finish all the allocation for those instructions. In this way, we change the shellcode constraints from sk is equal to 2 previously and to sk plus 3 is equal to 2 because we move the position of the second instruction. However, layout remediation may fail. And this is because when we add those jump instructions and when we skip those memories that might be contradict with the path constraints, we somehow miss many spaces. We resume them, and in the end, we may do not have enough space to put all the instructions in the shellcode. In this way, we'll look back to the path constraints and to find out those superfluous constraints and try to see how we're going to resolve them. And we call this step as path knitting. Path knitting also starts with adding the shellcode instruction one by one. But the difference is that when there is no satisfiable solution after adding a particular instruction, we identify the conflict constraints using unset core, and we find out the branch that introduces this conflict constraints. And then we start path exploration starting from this path. When we do path exploration, we're restricted by requiring that all explored paths can only deviate once. If the original path takes one branch and the explored path takes another branch, we say the explored path deviates from the original path. When the path joins together, the explored path must follow all the rest of the branches that the original path takes. For example, if we start with path exploration at this if statement, and one possible path is to say if sk is not equal to 1, so we will not call the function blah, and we go to the vulnerable function. In this way, we change the path constraint from sk is equal to 1 to sk is not equal to 1. And now the path constraints are no longer contradict with the original shellcode constraints, and we are very happy. Okay, to evaluate our work, we got 20 original exploits from the Cyber Grand Challenge. And meanwhile, we have 5 pieces of new shellcode in different length, in different numbers of instructions, and created by different authors. In total, we have 20 times 5, which is equal to 100 different cases. We found that while previous work is able to generate 31 exploits, ShellSwap generated 85 exploits, among which 57 exploits are generated by layout remediation, and 28 more exploits are generated by path knitting. Our evaluation showed that ShellSwap can generate 2 times more than previous work did. And both layout remediation and path knitting are necessary. We also evaluate our system ShellSwap in terms of the performance of generating those new exploits. And we show it in this chart. The x-axis are those exploits sorted by time in ascending order, and the y-axis is the time spent in seconds, and it's in logarithmic scale. For all exploits, we found that more than 70% of those exploits can be generated within 3 minutes. And this means that if you spend 3 minutes, just wait there, sit there, or, well, get a coffee, tea, whatever. When you come back, you get a new exploit. And this is much faster than human analysis. Okay, in conclusion, we show that reusing control flow hijacking exploits can be done automatically. This is possible, and symbolic execution plus our 2 method makes this possible. The first method is called layout remediation, basically to change the layout of the shellcode and thus change the constraints caused by the shellcode. And the second approach is called path knitting, which is to change the path executing and leads the program to be exploitable. And in this way, we change the path constraints. We propose system ShellSwap, which is able to generate 85% of the new exploits. And among them, 70% plus of the successful exploits can be automatically generated in 3 minutes. Thank you. Yep. Question, please.
Yes. Hi. This is a very interesting work. I have a question about the path knitting.
Yeah.
So you do path knitting only when you can't find a satisfactory solution to the constraint. So why don't you do that proactively? Because if you know the control flow graph, then you'll know which branches are the prerequisites for reaching the vulnerable statements and which conditionals are unimportant. So if you remove all the unimportant branches, then that would make your the constraint solver much easier. So have you thought of that?
So for us, I think the problem is we don't know which function is the vulnerable function. Well, we don't know how to reach this exploitable state until we do the symbolic execution. So after we finish this symbolic execution, basically we go for only one trace because we have the original exploit, this input, and we don't explore all the possible paths. We just go through the particular branch instructed by the original input. So at that point, we don't know what other branch are important or not, which is the reason why we started the exploration based on the unsatisfiable point, and we try to just walk around and explore a little bit. But we want to avoid, or I shouldn't say avoid, I should say mitigate the possible path explosion, which is the reason why we say the new explored path has to deviate once only.
But when you try to solve the constraint, you found that it can be solved because there's a conflict.
Yes.
So at that stage, why don't you remove all the conditionals that are unimportant for going down this path?
Because I don't know what conditions are important and which conditions are unimportant. What I only know is what constraints are conflict, or what is the unset core for solving these constraints. And to figure it out which is important or not, that is exactly what path meeting does.
But if you have the control flow graph, you know
Yes.
that information, right? Because
you know the branch. Oh, sorry to interrupt. I mean, you know the branch, but you don't know which one is important.
okay, maybe I should take this offline. Thank you.
Yes, let's talk it.
Joe from RSA Labs, very interesting work. I have a particular question about how the original exploit authors react to your approach. So what if the exploit authors think their code is their very important property? They want to protect their code from being analyzed by your approach. Like, I don't know, they do maybe some kind of obfuscation. So have you thought about this? Is it a real issue, or I just want to get some comments on that?
Yeah, so this is a good question. It's possible that the original attackers do some encryption or obfuscation in order to mess up our method. And we don't have the evaluation in this regard, but I think this is actually an interesting direction to look in the future. And actually, we have our going work in terms of this particular direction, and hopefully we can get accepted somewhere else in the future.
This is very interesting work. I have a high level question.
Yeah.
And in the real world, I just wondering what's the real world impact of the new technique. And have you seen in the real world the attacker continuously change their shellcode, just winning the same exploit? And from the defender viewpoint, shouldn't it be easier just go for the exploit itself? And in this way, you just shut down and prevent all kinds of shellcode to be executed, right, once the attack happens. That makes sense?
Yeah, I mean, this is a possibility, which is attacker will continually change their shellcode.
Have you seen these things in the real world?
I haven't seen this in the real world, but
Yeah.
I think maybe this based on my limited experience on the.
I can see these things for the CTF. This is very
Yes.
useful.
Well, the thing is, yes, CTS is probably a using scenario for this regard, but also what we want to. I think what part of the goal for this research is to inspire people that, hey, next time when you attack, you need to think about the possible technique that people may come up with attack right after you and attack back to you, and this comes to the collateral damage. And actually, we do have some research based on the collateral damage, and we have some interesting game theoretical observation based on the existence of such piece of technique.
Thank you.
Thanks.
All right, let's thank the speaker again.
Thank you.